All right, so here we go, second half of the unit. And today we're going to look at some pretty cool stuff, I think. We're going to tie this back to stuff that you've done all the way back in grade 10, some pretty big ideas, but we're going to extend this to some pretty cool new places as well. So let's start by revisiting grade 10. A lot of this is going to be visual. We're going to visualize some of this together, but it's your success is really going to come down to your willingness to visualize these things, think about these solutions, why they make sense, why they are what they are, that sort of thing. Okay, we're going to do a couple of days on just intersections of lines before we get into some other even more cool and more new areas. Intersections of lines is things we've already done. We do this in grade 10. So this is in some ways not new in that sense. This is grade 10, but obviously when we get to three space, that is going to be new, okay? And then just new notation, vector notation, parametric, that's all, that part of it is all gonna be new. All right, let's get into this. From grade 10, when two lines exist in two space, we have, what do we mean by three possibilities? We mean, what are the three different types of solutions that we can have? Okay, that's what we're talking about. So it's really helpful to know ahead of time what the possibilities are. And that's a big part of that is because sometimes we get these solutions that seem strange. Like when we're solving these algebraically, the solution looks like it doesn't make sense, looks like we made a mistake. But if we already know what the possible outcomes are, then we can interpret our solution, our algebraic solution. And one of the themes that we're going to notice through all of the second half of this unit, whether we are looking at lines or planes or what have you, is that interpretation. Okay, it's a huge part of what we're going to be doing and looking at, and really the focus of almost everything we're going to do is we're going to do a bunch of algebra, but then we're going to say, what is the interpretation of this? And in some cases, it's going to be, what's my next step? But in other cases, it's our interpretation is just going to be the end of it. It'll just be the solution. Okay. And in that interpretation, as I said, it is going to be crucial to have advanced knowledge of what the possible outcomes are. So in two space with two lines, as we've already said, there's only three possibilities. That's not too bad, okay? But what are these three? From grade 10, can you remember what they are? It's been a while, I know, and it's not something that's come up a lot, so maybe this isn't fresh enough in your mind, but I want to give you a second to think about this. What are those three possibilities? Okay, so the first one is simply, I think, they cross at a point. Here's my two lines, okay? So they cross at one point. And there's one solution, which is the point where they cross, okay? Um, a, a big part of what we're gonna do is the geometric interpretation, but that includes the description. How many solutions are there? What does that solution look like? In two space with two lines, this is just the grade 10 version of all of this. But once we start extending this to the grade 12 version and in three space and with planes, we're going to see that our world grows a lot, okay? So just this part, just that description, they cross at a point and there is one solution. Turns out that's a pretty big deal, being able to say that, okay? Being able to interpret two lines crossing at a point and describing that is a good step in the right direction, good first step, okay? What is another one of the possible the three possible geometric interpretations of this. Okay, I could have, whoops, I'm going to try to use the same colors. That might be too thick. I'll just use a regular one. Hopefully that shows up. But as you can see, I have two lines on top of each other. Okay, I'm going to maybe make them both, whoops, a little bit darker so they show up a bit better. Okay, and this is called parallel and coincident. Coincident is a fancy way of saying on top of each other. Okay, they're saying they coincide, they exist in the same place. People cannot coincide with each other because it would literally physically be taking up the same space. Okay, um, but lines can. So these two lines are parallel, but even more importantly, they're coincident. So they are taking up the same space. And um, there are infinitely many solutions. And the solution is the lines. Each of those lines, they're the same line, really. They would have probably equations that look different. One would be, we would kind of think of it now as a scalar multiple of the other, or just a multiple of the other, because we're not talking vectors yet. But we could think of it that way. So they are the same line, but their equations might look different. But the point is that there are infinitely many solutions, but the solution is that line, right? Although generally speaking, we would just say infinitely many solutions and then stop at that. And then the third possibility, again, try to think of these on your own, because this is what it's going to come down to, is thinking of these on your own. Okay, so this is similar to the second case that we had there, but now we're going to have two lines, because this is always a system of two lines, right? But these are parallel and distinct. Okay, so parallel and distinct. And how many solutions? No solutions, zero solutions, or just no solution. So in the first case, we have one solution. In the second case, we have infinitely many solutions. In the third case, we have no solutions. This is going to be a big part of one of the things that we're going to be looking at over the next several days is when we say interpret, geometrically interpret the system, we mean part of that is how many solutions are there, okay? And so one solution, in this case, one solution, infinitely many, or no solution, those are sort of your three options. There are three possibilities. In some cases, you may only have to describe the solution and state how many solutions there are. And in other cases, you will have to actually find the solution. So if there is one solution, they cross at a point, you'll have to find that point. And that's what we did in grade 10. So that's not strange. But we will see after we've done all the different kinds of systems that we're going to do in this course, we will see that our approach is a little bit different in terms of all the different possibilities. And sometimes we're not looking for the solution, we're just trying to describe the system. All right, so let's take a look at some of these possibilities. Let's take a look. The other thing about this, okay, today and tomorrow, we're looking at systems of just lines. And one thing that we have to get used to is whether we are given the equations in vector form, parametric form, symmetric form, scalar form, if we're talking two space, right? There's all these different possibilities that we could be given the equations of the lines, and we have to know how to solve all of them. And this part is different from grade 10. It's not the same, okay? Not only are we figuring out how to solve, but how to interpret the algebra as we are solving. Which of those three, in two space we're talking right now, which of those three possibilities we're looking at, okay? Um, I said this before, parametric equations are really awesome. They're really useful. And we're going to start to see a little bit of why. And so both of these are given in parametric form. Okay. And if that's the case, and I'm going to solve it this way, if it was scalar, you could solve it the grade 10 method. Substitution or elimination, right? That's something from a long time ago. We all know how to do that, hopefully. Or if we don't know how to do it right now, we can refresh ourselves and we can figure that out, okay? And so with scalar form, you could do that. But if you're in parametric form, then we have another way of doing it. Well, these are already solved for x and y. So we just set x equal to x and y equal to y. Okay, because if we're talking about a system of equations, we're talking about the same x and the same y. But the way we organize our solution is going to be a little bit different. So over here, I'm going to talk about the x's. So I've got this x and this x. 2 plus t equals 1 minus 2m. Okay, and then what about the y's? I got negative 9 plus 4t equals 9 plus 3m. So what do I have now? I have a system of equations in two variables, but my variables are t and m, not x and y. But I still have a system of equations that I would solve, as I just said, with substitution or elimination. Okay, so that is still what we're going to do. It's just that the variables that I'm solving for now are the parameters of the original equations. And one of those equations, in this case, the parameter was t. In the other case, in line 2, it was m. Often we see s as one of the parameters. But anyway, regardless of what they are, I've got a system of equations in two parameters, and I'm just going to, or sorry, in two variables, two equations, two variables, and I'm just going to go ahead and solve. Okay. So how do we do that? We call one of them equation 1 and one of them equation 2. And I'm either going to use substitution or elimination. Okay. And so in this case, I am going to look at the t coefficient, and something that we've talked about a lot last semester in MHF and this semester in this course is efficiency. And so I am going to sort of develop my own little system here of how to solve these. That's going to work in the same number of steps, and it's going to be direct every single time. And I'm going to just kind of, it'll be, even be showing my work exactly the same way every single time. And the only reason why I'm doing this is because it requires less thinking. What we're going to notice is when you are given this kind of a system and we're working with the parametric equations, what we're starting with is going to be the same or almost the same every single time. So having a system that always works will be good. So what I'm going to start with is I am going to multiply equation 1 by negative 4. Okay. And that gives me negative 8 minus 4t equals negative 4 plus 8m. So I multiplied negative 4 by that whole equation, and that just meant every coefficient was multiplied by negative 4. Now, the reason why I did that is because in equation 2, I'm just going to rewrite it. I've got negative 8. I've got plus 4t equals 9 plus 3m. Now I've got the t coefficients both as 4. And so I'm going to eliminate that one. Now, again, I like to have them be the same but opposite signs, because then I'm adding, and adding is almost always easier than subtracting. And that's why I multiply by -4. So you're going to see that common pattern over the next little while that I'm going to do that basically every time. There's a reason why I'm doing that. You don't have to do it exactly like me. You don't have to do it that way. But you know what? Honestly, it's a really useful thing to do. It is often easier, almost always easier to add than it is to subtract. Okay. So now I am going to add these together. And so here we go. -8 plus -9 is -17. -4 plus 4 is 0. -4 plus 9 is 5. Equals. And 8 plus 3 is 11. And I can do all of that in my head really easily. I can subtract in my head as well, for sure, but I'm more likely to make an error in the negatives, that kind of thing. Now I'm solving this for m. So I'm moving the -5 over. I'm going to subtract 5 on both sides, obviously, and I get -22 is 11m, so m is -2. Okay? And that means, here's my interpretation, therefore, the lines cross when m equals -2. Okay? And maybe that doesn't seem obvious, but once we get into more of these, then we will, then you can trust me, you'll believe me that that's what this means. If they didn't cross at one point, I would have gotten a very different solution there that I would have to interpret at that time. Okay, so and we're going to talk about that in a second. So if I'm solving for one of the parameters and I get a value of the parameter, in this case -2, that means we are in this first case, case 1 in this description here, where they cross at a point. One solution, that's what we have. Okay, because I happen to solve for m, well, I'm going to be subbing into equation 2, because that's the one that has m in it. So I'm just making a note of that. This is just to myself. So must use equation 2, or line 2, sorry. Because, or sorry, not the y equation. I'm circling the wrong one here. Line 2, because that's the one that has the parameter m, right? So that's the one that we have to use, line 2. Because we don't actually care what m equals. If we are solving the system, we need to know the point, and the point is x and y, right? So how am I going to find that? I'm going to find x is equal to, in parametric form, let me just go back up here, 1 minus 2 times m, which is 1 minus 2 times -2, right? Because m is -2. So see what we did there? We found the value of the parameter that is going to make this true. So I'm just subbing it in and solving. So that's 1 plus 4, which is 5. And y is equal to 9 plus 3m. So 9 plus 3 times m, which is -2, which is 9 minus 6, which is 3. Okay? Therefore, line 1 and line 2 cross at one point, a single point. They obviously don't cross at more than one point, so cross at one point, or at a point is fine to say. Cross at a point. There is one solution, and the solution is, or they cross at 5, 3. Now, this question just said investigate. We're going to get very particular about our instructions and expectations for our instructions. This one just said investigate. Okay. Oh, it did say determine the solution if there is one. So I had to find the solution. I'm not just interpreting what's going on. But the instructions are going to be very specific, and it's going to say things like, or something along the lines of give a geometric interpretation. And when a question asks that, I'm doing that right here. The lines cross at a point. There is one solution. Give a geometric interpretation, state how many solutions, and if there is a solution, what is it? 1, 2, 3. In some cases, we're not going to have all three parts because there might not be a solution, but that's the goal for these questions in general, is often to give all three of those parts as my solution. Okay, so be thinking about that. And I want to be very explicit. I don't want to leave any part out. I don't want to, word it in my own way. That doesn't actually mean the same thing. Okay, so we're very picky, very particular that you state all three parts. They cross at a point. That's the geometric interpretation. How many solutions? There is one solution. What is the solution? In this case, it's the point 5, 3. All right, so hopefully that is good. What we got from that is, yes, this question happened to give both lines in parametric form, but if they weren't in parametric form, I could just put them in parametric form and solve the same way, and often that might be what you're going to do, okay, so keep that in mind. But we noticed what it's like solving in parametric form. You solve for one of the parameters. In this case, we got a solution, and then this is how we interpreted that solution. Okay, that's what we're getting out of this. Otherwise, it's the same as grade 10. It was 2 lines and 2 space. So here are our other possible outcomes that we have when we are solving in parametric form, okay? And let's say the parameter we solve for is t. In the case above it was m, but let's just say it was t. We might get this, 0, t equals 0. Okay, I got 1t, or 1m, equals 2. So I just got something that makes sense. Or what if I got like 5t equals, whoa, what happened there? Equals 10. Well, then t equals 2, right? I'm just not done yet, but we're always going to end up with, let's say, 1t equals some value, okay, something like that. So that's what we got in our solution. I might get 0t equals 0, or I might get 0t equals k, where k is some non-zero constant. So k is anything other than 0, okay? Okay, so these are the other two possibilities that we might have, and these are, again, straight out of grade 10. We already kind of have seen this. We have seen these. We haven't seen it in parametric form, but we have seen these before. When we get these kinds of wonky things, we can interpret what it means, okay? And the way I like to think about this is 0t equals 0. This is always true. And 0t equals k. This is never true. So if 0t equals 0, and it's always true, then our interpretation, our geometric interpretation, is they are parallel and coincident. Now this word is going to be important, okay? Coincident, that's what we say, because it means they're coinciding. It means they are on top of each other. They're the same line. They occupy the same space. That's what the word coincident means. Okay, so that's the geometric interpretation. They're parallel and coincident. The number of solutions is infinitely many. And those are two of the parts, probably, of my answer. If I'm asked to state the geometric interpretation, then I say parallel and coincident. The number of solutions, infinitely many. Okay, and then in the other case, if 0t equals k, then they are parallel and distinct. And there are no solutions, or no solution. Okay, 0 solutions. And so that's the number of solutions is 0, and the geometric interpretation is they are parallel and distinct, separate. They're different lines, okay? We can think of that visually, but that's the description geometrically, okay? So this is nice because this gives us a straightforward prescriptive system to follow. I solve the parametric forms by setting x equal to x, y equal to y. And even if I'm not given parametric form, I can convert to parametric form and do the same thing. And depending on which of these situations I find myself in, I can interpret the solution and kind of figure out where to go next. I may have something else to do, or I may not. Okay, and again, that's going to be a common theme. We often do a first step, and we do some interpretation based on the first step, and that is going to kind of tell us what to do next. Okay, we're gonna, and that might seem a little cryptic right now, but you're going to see what that means as we do more examples moving forward. All right. Example 2, determine the number of solutions to the system without solving. That's interesting. So I've got 2 lines. I could call this L1 and L2, right? 2 lines. How do I know they're lines? They each only have one direction vector. Also, they're only in 2 space because it's X and Y, no Z. Okay. It seems obvious as we're working through this stuff, but trust me, once we dive into this and we start matching questions, it will not be, until we gain that experience, it will not necessarily be obvious that we're looking at lines or looking at 2 space or 3 space. I mean, once you think about it, it might be obvious, but until we gain that experience, it's not necessarily always going to jump out at you. So it's something worth pointing out. Anyway, what does it mean? This is another thing. Oh my gosh, there's a lot of, not only are we learning how to do all of this math and the algebra, but we're also learning all of these sort of specific instructions. So this one's different because it says do not solve. And so when we say do not solve, depending on the situation, it's going to look a little bit different, but it basically means you can't do this, right? You can't just find the solution, interpret the solution, and then not state the answer. So what are we going to do in this case in terms of how could we just determine the number of solutions? So it's either, what are the 3 options? One solution, infinitely many, or none. How can we figure out which of those 3 possibilities we're looking at? This might require more than one step, depending on the situation we find ourselves in. But the first step of it is something that I think is really important, and it's something to always be thinking about. What if we look at, like, think of it for yourself, if you can, but what if we look at just the direction vectors? Okay, so I've got line 1 and line 2. What's direction vector 1? It's negative 3, 7. What's direction vector 2 of line 2? It's negative 6, 14. What do you notice about those direction vectors? I hope it's jumping out at you. They are scalar multiple of each other. 2 times direction vector 1 is equal to direction vector 2. Therefore, they're parallel. Okay? But that puts us in one of these 2 possibilities. They're either parallel and coincident or parallel and distinct, but we don't know which of those is true yet. Okay? So we still don't know if they are coincident or distinct. Okay? How, without solving, how are we going to figure out which one of those it is? So it's either no solution or infinitely many solutions. That's what we had to figure out. Without finding the actual solution, without doing what we did above, how are we going to do that? Well, I can take a point that's on one of the lines, check it in the other line. If it's on the line, they're coincident. If it's not on the line, they're distinct. I mean, if these are parallel, either all points are on both lines or both lines share no points because they're parallel. And we're only talking two space here, right? So how do I get a point on a line? I'm going to check the point that the position vector of one of them goes to. So in this case, I'm going to use this point, which I got from the position vector. Again, this is a vector, okay? But I've turned it into a point by writing it with round brackets. So I'm going to check that in L2. I'm going to check the point that I know is on one of those lines, check it in the other line. How do we check if a point is on a line? That is something we have done. One is the x value minus 5 minus 6x s. Okay. And then for the y's, sorry, what am I doing here? 1 equals negative 5. So I'm checking it in line 2, and this is the x part of line 2, right? And then the y is the y part of line 2. So 5, the y coordinate, equals 19 plus 14s. What do these s's mean? Okay, so I'm going to move the 5 over. I'm going to solve for s. I get 6 equals negative 6s. So s is negative 1. I get negative 14 by subtracting 19 from both sides equals 14s. So s is negative 1. What does that mean? We've done this before. We've talked about this. Consistent parameter, consistent s. I already know that point is on the first line. Now I've checked it. It's also on the second line. Okay, so therefore, the 0.15 is on line 2. Therefore, line 1 and line 2 are parallel and coincident. And there are infinitely many solutions. So this just said determine the number of solutions, but it might say determine a geometric interpretation and the number of solutions, that kind of thing. So again, there's two parts. Parallel and coincident, that was one of the parts. Infinitely many solutions, that was the other part. Yes, it's true that you just have to answer the questions explicitly that you're asked. That will be the case if you're ever unsure, especially while we're just doing the practice. Ask, what does my solution require here? Okay. When in doubt, I guess state more information than you're asked for. But we want you to know what you're being asked. What's important here is it says without solving. So it really is important that I didn't do this the same way I did up here. We don't want you necessarily to just always take parametric form and set them equal to each other, because we want to push you to think about the direction vectors in this case. And there's a great visualization if you look at these two graphically, or there's just a great understanding of lines and vectors, direction vectors, all that stuff, of that the fact that these two direction vectors are collinear, and then checking one point and the other. Like, there's just a lot of deeper understanding in that, in what we've done in example 2 here, than just that, right? Just looking at the parametric interpretation kind of thing. So that's why we sometimes ask these questions in different ways, and we expect that the solution is presented differently because of that reason, because it does require a different type of understanding. Keep that in mind, because that's going to be the same for all the things that we do, all the different kinds of systems we're going to look at. Okay? All right, so we've done 2 of these. Now we're going to jump to 3 space. We're going to open our world again. And turns out there are 4 possibilities in 3 space. Now, what are the four possibilities? Well, one is they cross at a point. So one solution. They could be parallel and coincident. Infinitely many solutions. So again, there's a geometric interpretation and the number of solutions, okay? And so those are two of the possibilities. The third is they are parallel and distinct. And there's no solution. And the fourth, I'm going to leave out for now because I want you to think about it. And I want you to see if you can visualize what would happen in three space. You could even guess and type it into, computer technology, whatever, GeoGebra, Desmos, whatever you want to use. You could probably figure it out. Type it in. If you pick two random equations, you'll probably get the fourth one, but maybe not. Okay, so I'm going to leave that for now. We're going to come back to that. So leave a space. We're going to come back to number 4, but 3 of them are the same as the 3 that we've done, and I hope that you can follow that. I hope that the visual side of that is reasonable to extend our understanding of 2 space to 3 space in this context. Okay, but the fourth one, I'm sure some people can visualize that and can come up with it and think about it. But don't forget, you would have to give a geometric interpretation and the number of solutions. So how many solutions would this other one have? And how would it be different geometrically? How would we describe it differently from the other 3? Because the number of solutions in one case and the number of solutions in another case, they might still be different cases. You may not be able to come up with the actual word that we use. That's fine. I wouldn't expect you to. There's a particular word that we use to describe this case, but also the number of solutions is an important part of it. Okay, so we're going to do some examples. We're going to see this case number 4 come up, and when it comes up, we're going to come back and fill this in. All right, so example 3, we still have a couple more to do here. And we're just going to start, taking every one of these, how are we going to approach it? And one of the first things I'm going to look at is what form am I given? So I'm given 2 lines. Moving forward, by the end of this unit, you will just be given questions and you won't even be told what they are. So you have to be able to identify them as lines or planes. I've said this all along. I can see that these are lines because they say L. How else can I see their lines? Each of them only has one parameter. How do I know this is 3 space? Well, there's X, Y, Z. Like these are all the different things that we do need to be picking up on and observing, noticing as we go. So I've got 2 lines, but they're in 3 space. One is in parametric form, the other is in vector form. And so in this case, and in some, like in different cases, there will be more efficient ways of doing these things. And it's not necessarily about right or wrong, it's about efficiency, okay? So try to think about that. In all the different systems that we look at, that's gonna be the case, different levels or different ways of being more efficient. One thing that I can do, and I think it doesn't take a lot of time, so I think it is an efficient use of my time, is rewriting in parametric form, because we've kind of already indicated that parametric form is useful. So this, once I am good at this, it is trivial in that it only takes 4 or 5 seconds to rewrite that out in parametric form, okay? And there's a good chance that I might need them, or I might want them both to be in parametric form, so that's done. But the other thing, in fact, I might have done this first, and the other thing that I think is an efficient use of my time is looking at the direction vectors. Okay, and this is kind of like the last thing that we did. So, but this means I have to know how to find the direction vector from parametric form. From vector form, it's easy. From parametric form, it's easy as long as I know what I'm doing. And why would I do this? Why would I take the time and do this? Do you have to write this? Some of you are already wondering. No, you don't. I'm writing it because I'm thinking about it. And why wouldn't I take a moment and do that? Because why would I? Well, if I notice that one is a scalar multiple of the other and they're parallel, I can maybe save myself the trouble of doing the bigger solution and just check if they're coincident or distinct, right? If I know they're parallel, then I know I've narrowed down the cases. And again, everything that we do, you're going to see this pattern of narrowing down the cases and like what is something useful that I can do quickly that will eliminate some cases and possibly at least eliminate work. And you know, is it worthwhile to do that? And that's the efficiency that we're talking about. And in this case, they are not scalar multiple of each other. So D1 is not in any way equal to any K value times D2. Therefore, they are not parallel. You do not have to write all of that, okay? These are the instructions I was talking about before. Give a geometric interpretation, step 1, okay? Whoops, 1. State the number of solutions, that's going to be step 2. And if possible, solve the system, state the solution. Determine, oops, 3. Determine and state the solution. That's going to be part 3, where it's appropriate, okay? So I don't have to necessarily communicate when I'm eliminating possibilities, but you might write this down. Of course, I'm doing it for the lesson because I'm showing my thinking, okay? But you don't necessarily have to show that as part of your solution unless it actually becomes useful, unless it becomes part of your solution. If they were scalar multiple, then you would say, oh, therefore they're parallel. Now I'm just going to check a point in the other line, and then I would know which case I'm looking at. But in this case, they are not parallel. Therefore, they are going to be one of these two possibilities. They either cross at a point or they're that case number 4 that we haven't actually identified yet. So let's take a look at this. And we're going to do the same thing. We're going to set the parametric equations equal to each other. And that's why I've already written this out. So I'm going to set the x's equal to each other. 3 minus t equals 7 minus 2m. The y's are 2 minus t equals 12 minus 4m. And the z is 28 plus t equals 17 plus 5m. Okay, so just the z equal to the z. No magic there, that's where that's coming from. Now, an important idea in mathematics is if I'm solving equations that have 2 unknowns, I need 2 equations. Now I have 3. I don't have 3 unknowns, I only have 2 unknowns, t and m. So I have more equations than I need, but it's going to be crucial that my solution satisfies all 3, okay? And I don't know that for sure. I don't know that it will. So I am going to have to, here's what we're going to do. And I hope so far, I mean, we're covering a lot, I know. We're going to do this again tomorrow, but, you know, make sure that you understand that in all of these cases, there is kind of an algorithm that we're following, right? Like there is a step-by-step, and I might say, okay, I'm doing it this way because I've already eliminated these ideas, or I've already kind of determined what this like what's happening in the situation, what these lines look like. Like I may have already kind of figured out what's going on, and that's why I'm doing things a little bit differently from a different question. But there is still a step-by-step algorithm for how to solve these. Okay. And so, and don't forget, now we're in three space. So this is different from the other two examples we've looked at because we're in three space. So in three space, they're not parallel. I set the parametric equations equal to each other, and I'm going to write down what I'm going to do over here. In this case, there's no magic here. I'm going to solve 1 and 2, but then I have to check that in 3. Okay, so it's not enough to just solve 1 and 2, and we're going to see that before the end of the day today. I have to check that solution that I get in 3 and make sure that it satisfies 3 as well. Okay, so let me go ahead and do this quickly. And I'm only choosing 1 and 2 because they're easiest. Okay, so equation 1 I'm going to leave alone. Whoops. 3 minus t equals 7 minus 2m. Equation 2 I'm going to multiply by negative 1. And again, that's just because I like to add and not subtract. And it's easy to multiply, whoops, although I just made a mistake. It's easy to multiply by negative 1. It's harder to subtract negatives, that kind of thing. Okay, so negative 12 plus 4m. And now I am adding these together. So I have 3 plus negative 2, which is 1. Negative t and t is 0. 7 and negative 12 is negative 5. And negative 2 and 4 is 2. All right, whoops, I think I have a mistake in here somewhere, possibly. This is supposed to be plus 2m. So that's plus 2m. All right. And this is minus 4m. Nope, that's minus 4m. So, no, sorry, that's plus 4m because it was minus 4m. And so this should be 6. All right. Sorry about that. I hope you can follow that. But I think I've got it right now. Okay, add 5 to both sides. I get 6 equals 6m, so m equals 1. Okay. I've got equation 1, 2, 3. I'm going to call this equation 4 because now I'm subbing 4 into equation 1. So 3 minus t equals, 7 plus 2 times m, which is 1, so 2 times 1. Solving for t. 7 plus 2 minus 3 is negative 6, positive 6. And so t is negative 6. All right, so I got a solution for m and t, and that looks similar to the first example that we did, and you might think, oh, that means they cross a point. Not necessarily, because all I have solved for is 2 of the coordinates, right? I've only solved for x and y. We're going to look at this deeper momentarily, but let's see what happens when I do this thing that I said before, where I check in the third equation. So I'm going to come over here, and I'm going to check m equals 1 and t equals negative 6 in equation 3, which in this case is z. So that is 28 minus t, which is 6, which is 22. And the right side is 17 plus 5 times m, which is 1, which is 22. Left side equals right side. Therefore, it satisfies the third equation as well. And I've got our solution. They cross at a point. Okay, there is one solution. Now, maybe I'm getting ahead of myself a little bit here because sometimes we might want to wrap all this up at the same time. But I think, while we're learning this is good to look at that, like, what have I discovered here? What's my interpretation? How far have I got here? And this is how far I've got. So I now know that they cross at a point because I got values for M and T. I didn't end up with these situations. Okay, so I got values for M and T, but then I had to check them in the third equation because we're in three space now. They satisfy that equation as well. So my interpretation is that those parameters for M and T, those values for my parameters of M and T, are where the solution to the system is going to occur. So I have one solution, cross at a point, but I have to figure out what that point is. So how do I finish that off? Well, I just find the x, and I'm just going to go ahead, and it doesn't matter which of the equations I use because I know it's going to satisfy both. So I can use line 1 or line 2. Okay, so in line 2, I've got x is 7 plus 2 times m, where m is 1, which is 9. I've got my y, which is y equals 12 minus 4 times m, and m is 1, and that's 8. And maybe I'm choosing m. I'm choosing line 2, which has parameter m, because 1 is easier to use than -6. But it really doesn't matter, right? You could use either. So, and then z equals 17 plus 5 times 1, or 5 times m, which is 5 times 1, which is 22. And therefore, the solution is x, y, z, right? 9, 8, 22. And that is geometric interpretation. Number of solutions. What is the solution if there is one? Okay, those three parts. I think that's good. I think we've kind of covered everything there. That's three space. That's why it's different from the other examples. Again, this is like an algorithm that you want to be familiar with. Just to recap quickly, I check the direction vectors. I don't have to show that. I check them because if they're parallel, I can probably save myself some work. If they're parallel, do I have to go through all of that? Okay, maybe I don't. But they're not parallel. I don't have to show that, but because I can do that by inspection so quickly, maybe it's worthwhile. I rewrote this one in parametric form because I want to use the parametric equations to solve. Okay, and it was given in vector form. So again, that was something I had to do, right? Like I had to know that. There's a lot of levels to this. I set the parametric equations equal to each other, came up with 3 equations, solved for 2 of the parameters, checked those 2 parameters in the third equation that I didn't use. Don't solve for 1 and 3 because they are easier numbers, and then check in 3. I solved in 1 and 2 and checked in 3. Or solve in 2 and 3 and check in 1, right? You've got to make sure you cover all 3 bases. Okay, hope that's clear. And that gave me my solution. And then I just subbed one of the parameters in to find the actual point. All right, I hope you've got that. I hope that's okay. We do have one more to do here. It's been a long lesson, but this is an important one, and this one's actually not going to take as long. So I want to just dive into it here, okay? And in this case, I'm given 2 in vector form, okay? And that's just, depending on the form that I'm given, my approach might be a little bit different, right? But hopefully it's not going to be drastically different. All right, so I am going to start by just inspecting my direction vectors. 0, 3, 2. direction vector 2 is 4, 0, negative 1, not scalar multiples of each other. So they're not parallel. Okay? If they're parallel, I can save myself some time, but in this case, they are not. So now I'm going to set my parametric equations equal to each other. Notice I'm not actually writing them out in parametric form because I think I can do that safely just in place. So this is 2 equals negative 3 plus 4t. Now hold on, somebody, whoops, 4t. Somebody might have missed what happened there. It's 0s. So that's why it's just a constant 2. As usual, there are all these little things that you have to be careful of as you're going through, you know, things that can be different, hiccups that when you're watching somebody else's work, you might miss as to why that was different from the last example. But that's why, okay? Hopefully you can follow that. And then for this one, I've got 3 plus 3s equals 1 plus 0t. So again, that's just equals 1. And then my z is 10 plus 2s equals 2 minus t. Okay, so I've got equation 1, 2, and 3. And you may have missed it, but something really important happened here, or something really interesting, something really useful happened here. Because of those zeros, it's because of the zeros. Can you pick up on what it is? Because you're going to want to, if this comes up again, or when this comes up again. Okay? And it happened twice, which is awesome, because that's what's going to save me a lot of time. This is no longer an equation with 2 variables. It's just an equation with 1 variable. So if I move the negative 3 over, I get 5 equals 4t. So t is 5 over 4. I can just solve for t. I didn't have to do the whole thing that I was doing before where I was actually solving a system. And because this happened twice, I can do this with both. So I'm going to subtract 3 from both, and I get in the equation 2 here, I get from both sides, right? I get 3s equals negative 2, and s is negative 2 over 3, right? So I've already found the t and the s. This is what I did before, but it took me more work because I had to actually solve the system. Just because of how this one worked out, I didn't have to do all that work. But what I end up doing is I find those values of s and t, those parameters in this case, and I just check like we did before. So I'm going to check s equals negative 2 over 3 and t equals 5 over 4 in equation 3. All right, so this is all the same. I hope you're following this. This is all the same as what we did before. Whoops, 2 over 3, which is 26 over 3. And the right side is, now I'm going to leave that for a second, okay? And I want to show you something that happens here because this is interesting. This is kind of what happened before, isn't it? So hold on a second.
Okay, so I've got this system. Those 2 black lines are our 2 lines. I've got the system drawn already, and you can see that it looks like they meet at that point. Okay, and I'm going to talk about what that point is in a second, but first I want to show something, because actually what's happening here is they do not meet at that point. And this is the difference of lines in 3 space, is that these lines are what we call skew. Okay, now it looks like the lines cross somewhere else, but as I pan around them, you can see that they don't meet anywhere. Okay, so they miss each other. But what I want to show here, what I think is interesting, and it helps us maybe interpret the algebra a little bit, is that it looks from this angle like they meet at that point. Now, that point is point A and B, okay? And so you can see I can turn them on and off. So one of them is A, the other is B, obviously. And look at those 2 points. They share X. They both have x equal to 2 and they both have y equal to 1, but they have a different z. That's why one is above the other. And it's neat in this program, you can kind of, compare it to the scale and see that that one that's above is about 8 2/3. It's between 5 and 10. It's getting up there, right? And when I look from above and I can kind of zoom in and see where they cross, it looks reasonable to say that that point would be 2, 1, right? 2 along the x and 1 along the y. Now, where did I get those points from? So now we want to remember that when I solved, I got parameter values for t and s. T was 5/4. S was -2/3. And I subbed those parameters into the equations to solve for x and y in each of the equations of x, y, and z, sorry, for each of the equations of the lines. And that's why the x and y are equal. Because when we solved this question using the x and the y parameter equations, right? I could have solved with x and z and got the parameters s and t, but we just didn't. Often we maybe just choose the first two, x and y, unless there's something easy about z or hard about one of them, avoiding fractions or some reason. So there's no reason why we pick 2 and not the other one. But again, the process is we choose to solve, and then we have to check it in the third to see what happens. But this is what happens geometrically, visually, when we check in the third and it doesn't fit the third. Okay, but again, it's neat if you look at the coordinates of a and b, and you can see that the x and the y are equal when I sub the parameter values I got while solving for t and s into the equations to get those 2 points. It's neat that that's what we are solving. That's what we're getting when we get those parameters. We're getting the solution just considering the x and the y. And that's why we have to check in z to make sure that we also have, that they also meet there and it satisfies z.
Okay, so this is the same system that we're looking at. These 2 black lines that we're looking at here are those 2 lines. Okay? Same thing. So what if I put the points, or the point on there? That's where the 2 lines meet, isn't it? Right? But watch. Whoa. What actually happened there is I was looking at them from the top and it looks like they cross, but they actually don't because of that z-axis. They cross in the x and the y, but not in the z. And this is that fourth situation where they're not parallel, but they are what we call them as skew. Okay, so these lines are skewed. So we're going to go back up and add that as our fourth case. But this is what's happening. And again, I think this is really cool because when I look at them from above, it looks like they cross, but they don't. Okay. And so when I get values for the x and the y that work, and I used those values to come up with those points where it looks like they cross, but when I check it in check it in z, we already did y, it's not consistent, right? Left side does not equal the right side. Therefore, line 1 and line 2 are skew. Okay, and there is no solution. Okay, so this is the fourth case. So let me go up and add that. Whoops, there we go. So we have 4 possibilities. They cross at a point, they're parallel and coincident, or they're parallel and distinct, or the fourth is the lines are skew, and again, that means there's no solution. Okay, so those are the 4 options that we can have And that's kind of the new one. And that's what it might look like. And there's a big thing about this where we have to know what that looks like algebraically, how to interpret that, how that comes out as we're solving, okay? How it's different from the other cases. Remember in example A above, I got a value for my parameters that worked, but when I checked it, it also worked in that one. And so they crossed at a point. But when I got values for the parameters, a solution for the parameters, and I checked it and it doesn't work in the third equation, that's telling me the lines are skew. And this is the visual of it. Again, I want to show that, okay? And hopefully looking at that in the augmented reality version worked as well, right? It looks like they should cross. That's why two of the parameters work. But then when you tip it down, you can see that they're actually not crossing in the third coordinate, right? Where the other one did. So that means they're skew, and the interpretation is really important. And then you just have to remember, we didn't see examples of this, but we'll do more again tomorrow, is, is this. When you set the parametric equations equal to each other, you're going to get, it, and they're parallel, okay, and distinct or coincident, you're going to get those kinds of situations, and then you have to be able to interpret those as well. Okay, and I think that kind of sums all of that up. Um, so while you're working through this, you really have to think about the different properties of, you know, in this case lines, but for everything that we're going to do when we do planes as well, the properties, what they tell you about the interpretation, the geometric interpretation, and then how you can use that to go on and solve if you have to, that kind of thing. Like there are really different levels to our visualization and understanding of what's going on in all of these cases. And it does take time to practice different questions, go through it. In the different cases, what does the algebra look like? What does the visualization look like? Like all of those different situations. There are just little differences, you know, in the algebra or whatever that that we have to observe, we have to notice, pick up on, right? And then as well, on top of that, all the differences, like if we're given vector form, parametric form, symmetric form, all those different things. And we're going to add onto it when we start adding planes into the mix as well, right? So there are a lot of different things going on, but ultimately we can break all of these different questions down into their different sort of step-by-step algorithms, like step one, step two, step three. We can get there, and these really do come down to procedures that we can follow to figure out what's happening, to get the solution, interpret the solution, everything that we have to do. Okay, so we'll take another day on systems of just lines. But you know, go back and think about the specifics of each case and how we broke down everything that was happening and started to draw conclusions on how the lines were interacting in that geometric interpretation, and just ultimately go back to what are the possible situations, and how, you know, when, if there are three or if there are four, depending on what you're looking at, what would they look like? What would the algebra look like? You got to know what the possibilities are, what the possible outcomes are. That's going to make it so much easier to interpret the algebra that you're looking at, or even just if you're looking at direction vectors that are parallel or not, that kind of thing. Okay, so it's a lot all at once, but it's doable. But we have to take it step by step, and we got to think about those properties and start to think about the possible geometric interpretations. Whoops, finished too soon there. I missed one, so I tried to wrap that up, but um, I actually missed this example. So let's finish this one, and then in the next video tomorrow, we're going to do a bunch more, and we'll talk about this all again. I know, like I said, there's a lot going on here. It takes a couple of days. And then it'll take a couple more days when we do some of the other systems that we're going to explore. And then hopefully, you know, after spending some time thinking about all of this, it starts to make more sense. So here's another system of two lines in three space.
Both are given in parametric form. Uh, and the first thing I'm going to do is compare their direction vectors. So direction vector of 1, and this is why when we talked about this, um, being able to determine properties from every different form, like being able to quickly remember that the direction vector from parametric form is the coefficients of the parameter. And I want to be able to do that quickly. I don't want to spend a lot of time trying to remember how to do that. So take a look. Scalar multiple of each other. Negative 2 times d1 is equal to d2. What does that mean? Therefore, L1 and L2 are parallel, is what that means. So now I choose to check a point on one of them in the other. So I'm going to pick whatever point, okay? So I'm going to pick 1, 2, -4. So that's a point on L1, came from those constants in each of the equations. And I'm going to check that in L2. And so I've got the x, which is 1, is equal to 2 minus 2t. I've got the y, which is 2, that's, okay, is equal to 3 minus 2t. So that's coming from there, right? That's that 2, because it is the y value. And then the z is -4, which is this, right? And so -4 equals 8 minus 2t. Quickly solve each of these. I've got -1 equals -2t, so t is a half. I've got -1 again is equal to -2t, so t is equal to a half. So far consistent t's, okay? And this one is -12 equals -2t, so t is 6. Therefore, the point 1, 2, -4 is not on the line. On line 2, sorry, I should say specifically. Therefore, line 1 and line 2 are parallel and distinct. And there's no solution. So remember how important it is to be able to develop a plan, which considers all the different possible types of solutions you could have. And what we have here is I have chosen instead, I could have just done the solving part of this, right? I could have just set the parametric equations equal to each other like we did above and just start solving. But I decided when I looked at these two and with inspection, I just decided, oh, I can see that the direction vectors are scalar multiple of each other. So I wrote them out and stated that they're parallel, and that would be a necessary part of your solution. You would have to do all of that, okay? Then check a point on one in the other. If the point is on the other and they're parallel, then all points are on each other. And if not, like in this case, then they're parallel and distinct. Otherwise, they would be parallel and coincident, and there would be infinite solutions, which would be the line, okay? But I have still said the full solution here by saying what the geometric interpretation is, they're parallel and distinct, and stating the number of solutions. I just can't state a solution because there isn't one, okay? And remember, another big part of this is including all of those little parts, all those little details of how you show your work, what that means, and then how you interpret that for your answer. And so is that less work than doing this? Up to you to decide. It's not better one way or the other necessarily. Um, The one thing to remember is sometimes you're told without solving, do such and such. So this is not solving. So you would be allowed to do that, or that's kind of what they would be expecting you to do, is just looking at direction vectors, right? But we've talked about that. Okay, so that is the third example, or the one that I missed, shows an example of what happens when the direction vectors are scalar multiples of each other and how we can proceed. And then if they're not the scalar multiple of each other, the last example showed us how we would proceed.